1, 2, 3, 6. If I give you a sequence of numbers, how can you predict the next number in the sequence? One way of doing this is to use Wolfram Alpha, a web application for performing calculations. Let's do it right now. So let's see here. Okay, this is Wolfram Alpha. Let me type in the, this is a web page, by the way, the web page for Wolfram Alpha, wolframalpha.com. Let me type in the sequence, 1, 2, 3, 6. I'll hit enter. I have to wait a few seconds while it makes the internet connection and it starts doing the calculation. Here it goes. And let's see, it gives me a lot of stuff that's not really relevant. But if I scroll down to the bottom, let's see, oh yeah, there it is right there. So what this is it gives me a possible continuation of the sequence. It says after 6, maybe the next number is 10, then 20, then 35, and so on. And it gives me a formula for the sequence. This is great. So let me point out, though, that Wolfram Alpha is not a search engine. What a search engine will do is a search engine can only give you results that somebody has already posted somewhere on the internet. Wolfram Alpha, on the other hand, calculates the results that you request. So if you're creative and you request a result that no one has ever thought of requesting before, then what Wolfram Alpha gives you back might be entirely new. It might be something that no one else had ever thought of before and no one has ever seen before. A simple search engine couldn't do something like that. Now, the idea for Wolfram Alpha came when Stephen Wolfram, the founder and CEO of a computer software company, was trying to teach his son how to use Mathematica. Mathematica is a computer programming language that he developed for doing mathematics. Let me show you. Let's see, so here's Mathematica right here, and I can enter a command like, let's see, plot 3D, square brackets, curly braces. The curly braces are really important. Negative 3, curly, comma, curly. Okay, excellent. Hit Shift Return, and there we go. We get a nice visualization of the mathematical function sine of the quantity x times y. That's really great, and it's really useful to mathematicians such as myself. Well, Stephen Wolfram was trying to teach this to his son, and his son was frustrated by the complicated syntax. Sometimes it has to be square brackets, sometimes curly brackets. You have to have commas in just the right places. The commands have to begin with capital letters. It's complicated. His son was frustrated, and he said, "Dad, why can't it work just like a search engine? Why can't I just type in what I want?" And his father thought, you know, that's a good idea. And that was how the idea for Wolfram Alpha was born. Interesting ideas often have small beginnings like that. Well, let me digress for a moment from Wolfram Alpha and talk about computer programming languages in general. You know, computers excel at performing repetitive tasks. There are two main ways to instruct a computer to perform a repetitive task. They're called do loops and while loops. A do loop instructs a computer to perform a task a limited number of times. Maybe you tell it to repeat 10 times, 100 times, or just some number of times instructed by the user. In contrast, a while loop repetitively performs a task until some predetermined condition is satisfied. And if that predetermined condition is never satisfied, then the while loop will keep repeating forever and ever. In other words, it's possible for a while loop to go into an infinite loop. That's not possible with do loops. Do loops only repeat a limited number of times, so they can't go into infinite loops. Well, infinite loops are undesirable. So one natural question is to ask, is it possible to write every computer program without using while loops, without admitting the possibility of there being infinite loops? Could every computer program be written just using do loops? It turns out that this question was answered by mathematicians back in the 1920s, long before the idea of computers was even invented. So what it was in the 1920s, a Norwegian mathematician by the name of Thorolf Skolem was interested in the mathematical functions that could be computed just by using do loops. Historically, these were called the primitive recursive functions. And Skolem thought that every time that he could imagine a mathematical function, that it seemed that that function was primitive recursive. Every time he thought of a function, he could figure out how to compute it just using do loops. So in 1923, Skolem proposed that all of the functions in mathematics can be computed by do loops, that all functions are primitive recursive. It was a fairly reasonable conjecture. It was about 5 years later that a German mathematician by the name of Wilhelm Ackermann proved that Skolem was wrong. Ackermann introduced what's now called Ackermann's function. Ackermann's function is a function of 3 variables, x, y, and z. It's calculated as follows. F of xy0 is just x plus y. F of xy1 is x times y. Now remember, back from elementary school arithmetic, that x times y, that's x plus x plus x, y many times. F of xy2, that's x to the power y. That's x times x times x times x, y many times. You see, Ackermann's function is calculated in stages. To calculate each stage, you just repeat the previous stage y many times. So f of xy3 is x to the power x to the power x to the power x, y many times. Ackermann showed that this function, the Ackermann's function, cannot be computed just using do loops. It's an example of a function that's not primitive recursive. This blew mathematicians' minds at the time because no mathematician had imagined a function this wild. And of course, it really disappointed Skolem. Okay. What does this have to do with Wolfram Alpha? Well, around 2004, I was working for Stephen Wolfram, and he was interested in creating a website where people could enter in sequences of numbers, and the website would give formulas for those sequences. Of course, the idea for this website was eventually incorporated into Wolfram Alpha. What Stephen Wolfram wanted to do is he wanted to systematically list all possible sequences of numbers, systematically list them and catalog all of them. Well, up to some point. Of course, there's infinitely many of them. But how do you do that? How do you systematically list all sequences of numbers? That seems like a really difficult task. You might think, well, we could systematically list like all of the computer programs for generating sequences of numbers. The problem is that an arbitrary computer program might go into an infinite loop, and that's a problem. So what are we going to do? What about the primitive recursive functions? What if instead we list all of the computer programs that just contain do loops? We know that those definitely won't halt, won't go into infinite loops. And we know from Skolem's experience back in the 1920s that almost every imaginable sequence of numbers is primitive recursive, can be described by a program that just uses do loops. You have to look extremely hard and extremely far to find exotic functions like the Ackermann function that aren't primitive recursive, that can't be programmed just using do loops. So there you have it. That's the idea. You can systematically list all of the practically useful sequences of numbers up to some point, because there's infinitely many of them, by listing just the primitive recursive sequences of numbers. Well, that's a great idea. So this idea, it's not fully implemented yet in Wolfram Alpha, but it does serve to illustrate an important point. And that point is that Sometimes you'll have academic researchers studying obscure topics, like the primitive recursive functions, and then, decades later, these obscure topics will have practical, technological applications. So if you were to ask me, where do ideas that lead to important technological innovations come from? I'd answer you, they come from unexpected places. Thank you.